Okay, ladies and gentlemen. Now, welcome back. Lesson 4, Magnetism, Lesson 4. Applications of particle deflection. Now, for this, you have to remember a current moving charge creates magnetic field. Charge moving and a magnetic field experiences a force. Oersted, moving charge creates a magnetic field. Charge moving magnetic field experiences a force. We talked about this yesterday. Absolute value F sub B equals Q V perpendicular absolute value of magnetic field. And we have to talk about absolute value because we can have a positive charge and we can have a negative charge, and we have positive direction and negative direction and attraction and repulsion. And anyway, it just screws you up. So draw a picture and figure out which way the force is going. And finally, oh yes, direction of force. Third left-hand rule. Okay, so that's stuff you got to remember. Should be nothing new here. You guys okay with that? Yes, silence, no silence. Okay, now. Two things you got to know about this, the aurora. Charged particles. Northern lights. Aurora borealis. As in boreal forest. Northern forest. Not certain where boreal comes from, but anyway. So, these are the northern lights you guys see if you ever turn off the computer games at night and go look out the window. Anybody ever look out the window at night? You see the green and yellow, green and blue lights? Okay. Now, what happens is you have the sun, and it gives off what we call solar wind. Now this is mostly electrons, hydrogen atoms, helium atoms. Sorry, helium ions. Remember, the sun is like 5,000 degrees Celsius on the surface. So that's real easy to ionize atoms. So it'll spit out positive and negative charged ions. Now, we tend to get these, this gets a little complicated, but we tend to get solar flares. FLA. There he is. Now, that's the sun's magnetic field creating, well, flares. They shoot off in bursts. And so that's why sometimes we'll get impressive northern lights, and sometimes they're pretty wussy, or you don't see them at all. Either way, these solar wind come to the Earth. Now, as I reminded you, the Earth is like a giant bar magnet, magnetic field. So we have a north pole and a geographic south, and we have a magnetic south pole and the north pole. Anyway, this solar wind gets deflected into the magnetic field. Now it's really quite neat. When the solar wind hits oxygen, it ionizes the oxygen and makes it red and green. When we get into atomic spectra, I'll explain more about the why, and we'll do some calculations for it. But if you look up and see red and green lights, that's oxygen being hit by the solar wind. Nitrogen, on the other hand, gives us blue and violet. Now you should see more red and green because there's more you should see more blue and violet because there's more nitrogen in the atmosphere. But we happen to be better at seeing reds and greens. Now, so far so good? All right. Now notice here how I drew it spiraling. What happens, these charged particles, when they hit the magnetic field, the magnetic field is big enough, say this is an electron, what happens with an electron? Third left-hand rule, the magnetic field is going in. Direction of travel is like this. The direction of the force will be down. So it should curve like that. What happens when it's going down like that? That's the direction of the force. In. So it should end up going in a circle of radius r. Now if it goes in perpendicular. If it goes in an angle, it'll spiral or corkscrew as it goes along. Now, here, we're going to talk a lot about this. Force magnetic. If it's spinning in a circle, what do we call forces acting in a circle? Force F sub c. Or QVB equals mv squared over r. Now, this brings back a lot of Math 20 stuff. Fortunately, you guys aren't having that look when I talk about centripetal force. I forget, may I see your formula sheet for a moment? Is centripetal force formula on your formula sheet? Poopy, it isn't. Poop, 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 poop. Now remember, I don't want you writing on this formula sheet because you need to use it for the diploma or test. Now, if you really want to write this formula on it, mv squared over r, I don't mind. I'll just have to give you a new formula sheet for the tests and quizzes. Okay? Now, typical question that ask on the diploma. If the above electron is moving at 2.38 times 10 to the 3 meters per second into a 1.13 Tesla magnetic field, B field, what is the radius? What's the radius of curvature? But I can't spell curvature, so we're going to leave it at that. So if the above electron is moving at 2.38 times 10 to the 3 meters a second into a 1.13 Tesla magnetic field, what's the radius? Yes, I know, 76 years old. Married twice, I want to say 3. I thought it was 4. Anyway. Brilliant man. He died on Pi Day. And no, I'm sorry, I forgot to bring in pie for you guys. Sorry? I should have, but I had a brain fart, completely forgot, and I didn't have time to make it last night. Anyway, now, moving on. What is the formula we're going to use? So R equals mv squared over qv. Now, can I simplify that? QVB, sorry. Can I simplify that? Stop. Put the calculator down. Can I simplify this? Yeah. How can I simplify it? Cancel out? 1v. V squared over v. All right? So R that's another way to write the formula. Okay? So plug in the numbers in. What's the mass of an electron? 9.11. You should just look that up. You shouldn't waste time memorizing it. 2.38 times 10 to the 3 meters a second. Charge is 1.6 times 10 to the minus 19 of a coulomb. And 1.13 Tesla. Somebody grab a Mr. Calculator and tell me what that is. What you getting?
Wasn't it really small?
I don't know. Minus 31 times 3 is something to the minus 28. Minus 28 divided by minus 19 is something to the minus 8.
Yeah, it's
1 point. 1.19 times 10 to the. Yeah. 1.19 something, 1.20 times 10 to the minus 8 of a meter. So that is minus 6. That's to minus 5 of a millimeter. That's really small. That's small enough we can do that, in a lab somewhere. Okay? Now, as an aside, before I go on, I want you to note MV, where have we seen that formula before? Momentum. So they might give you the momentum of an item, of an object, not the mass and the velocity. Right? Now, so far so good? Now this leads to the second part, which I did as a handout for you guys to fill in. These are notes. I don't want to see them. All right, don't pass it back. Now, version 2. It's open. Now, applications of mass spectrometer. J.J. Thomson, the 8 of spades, used electric and magnetic fields to determine the charge-to-mass ratio of electrons. Why is the charge-to-mass ratio important? Oh, this was the video we didn't watch. Okay. Oops. Okay. So give me a moment. I'll see if I can find that video. Might be easier if we watch that. Yes, you may. Can I pause this?